My name is Michael McClellan, PhD student in physics at University of New Hampshire, and today I will be presenting on dynamic nuclear polarization at University of New Hampshire, vector and tensor polarization extraction from line shape analysis. Our goal is to develop a solid polarized target to be sent to Jefferson Lab for beam time to measure spin structure and tensor spin observables, such as AZZ, T20, and B1, to help distinguish between virtual nucleon and light cone nucleon-nucleon potentials, between hard and soft deuteron wave functions, and maybe provide an unambiguous signal for the detection of hidden color. Our lab has successfully dynamically polarized deuterated targets of chemically doped polymers and alcohols, and our next goal is to polarize deuterated ammonia and reach tensor polarization of at least 35%. Our lab is focused around a 5 to 7 Tesla superconducting solenoid electromagnet, into which we put our targets for polarizing, which we monitor with a Lanel VME-based NMR system. The magnet is cooled by a 1 Kelvin liquid helium evaporation fridge that is designed and maintained in-house. Liquid helium is pumped into a tank surrounding the magnet, and the fridge system makes a liquid helium bath that the target is submerged in. This bath is then cooled through evaporation to just above 1 Kelvin. We also use a novel solid-state millimeter wave system to enhance polarization, and we're the only lab that currently uses such a system for nuclear physics targets. We also have a fleet of 3D printers, which we can use for rapid prototyping and testing of parts. Our target ladder is 3D printed, and we've also printed O-ring components, spacers, housing for a power supply, and even a tabletop Hallbach magnet setup. Our prints have survived 1 Kelvin cryocycling and high radiation exposure. We detected our first polarized deuteron signals on September 10, 2020 in tridal-doped d-propandiol, and after enhancing the signal with our millimeter wave system, reached vector polarization exceeding 30%. We subsequently observed deuteron signals on multiple occasions, both in d-propandiol and in d-butanol. We have also performed hole burning with noticeable effect. Analysis is still ongoing, but similar techniques used by University of Virginia have resulted in tensor polarization of 36%, and we are working to replicate and confirm their results. We have also performed EPR, or electron paramagnetic resonance. We have been able to determine that the EPR line shape is dependent on the dopant used rather than the material. This will be of use in refining our RF enhancement for DNP. My personal contribution to QNH DNP has been an analysis of the deuteron line shape. Per Dooley et al., once a background curve has been subtracted, the signal can be fit to a known function with several physical parameters. Of most importance is R, which represents the polarization asymmetry of the signal, and can be used to determine both the vector and tensor spin polarization as long as the signal is in equilibrium. This is helpful in cases where a TE signal cannot be found and can be used to cross-check the area method. Thus far, results from this curve-fitting technique have matched nicely with the established area method. We have also been simulating signals in preparation for deuteron physics. To measure tensor polarization, we need a material with quadrupole splitting like ammonia to get distinct peaks for different spin state transitions. By modeling different quadrupole angle distributions, we can produce different expected signals. We have discovered that a sine function distribution best matches pre-existing data, but we are still unsure why, and further research is needed. If we can manipulate the quadrupole angle distribution, it could be made easier to analyze NMR data and also achieve a higher tensor polarization, so this will be also part of our research. For future cooldowns, we want to reach at least 35% polarization. To that end, we are hoping to build a rotating target cup and continue with hole burning and EPR. We also want to polarize deuterated ammonia and incorporate hole burning into the curve-fitting analysis so that signals out of equilibrium can be analyzed. We also want to continue with simulations to determine if the material can be manipulated for easier analysis. We are hoping to hold at least one more cooldown this year, and we hope to ship our targeted JLab for beam time sometime in the next few years. Thank you.